All right, well, it looks like the number of people in the lobby is slowing down a little bit, so I think we'll go ahead and get started. So my name is Jocelyn Backman. I am here on behalf of Applied Nanotools, and I'm today's moderator for our LAB2FAB workshop seminar. So as you may have heard in the last seminar, we have switched to some virtual formats to lead up to our workshop, which is happening now in Whistler, BC on September 25th. So we're very excited for that. We will continue to have monthly seminars virtually until that day. So at the end, I'll show the schedule for our upcoming talks. Today we have 3 speakers joining us. We have Philippe Babin from Photonics. We have Lucas Krostowski from the University of British Columbia. And we also have Pierre Barini from the University of Ottawa NanoFab to tell us a little bit about what they're doing over there. So before we get started with our speakers, I'm just going to give a brief overview of our LAB2FAB for those of you who might have missed the first seminar. So the LAB2FAB workshop is essentially a gathering for industry, academics, and government labs. And what we want to do is create an environment where we can nurture partnerships between all these stakeholders and try and improve outcomes for Canadian businesses, build that capacity, and ensure that Canadian businesses and academics have access to all of these government labs that have amazing resources that we may not necessarily all know about. So we're trying to make sure everyone has a chance to work together and really boost our Canadian ecosystem in terms of manufacturing and fabrication. And we also this time at the LAB2FAB workshop are having a special focus topic on photonics. And so the session that will be happening at the workshop is called Photonic Integrated Circuits, a Flourishing Canadian Ecosystem. So we will have, today's speakers are actually all giving sort of photonics-based talks as well. So this is a perfect chance for us to sort of see a preview of this session at the seminar or at the workshop in September. And we'll have opportunities to hear from academics, government, and industry who are all in this field, learn about some design and fabrication opportunities in Canada, and a chance to network with other professionals in the field. So this could be a great chance for you to make some connections for your business or for your future career. So just a little highlight of one of the special sessions that we will be having at this year's LAB2FAB. And I also want to take a chance to thank our sponsors for today. So our gold sponsor for this workshop is Lucida Photonics. Our silver sponsor is Photonics. And thank you very much to our sponsors today. We also have our lab sponsors, which is 4D Labs at Simon Fraser University, 3IT in Sherbrooke, TNFC in Toronto, and the Canadian Centre for Research in Photonics at the University of Ottawa. We also have our co-hosts of this workshop, the Stuart Blesson Quantum Matter Institute, or QMI, University of British Columbia, LAB2FAB, and of course, CMC Microsystems. And so with that, I think I will turn things over to our very first speaker. So as I mentioned, today's first speaker will be Philippe Babin from Photonics. He is the president. Over to him to get our workshop started. So Philippe, you are up.
So thanks for the introduction. Today, I'll be basically giving a presentation on who is Photonics, but I will do something that I've been often asked about in the making of Photonics. So there'll be a brief presentation on how we came to who we are right now in light of the multiple collaboration that we went through. I will then do a presentation on our technology, so explaining the basics of what we're doing and what we're looking after. So, and again, thank you so much for the opportunities. If my screen doesn't show properly, please let me know, but I'll keep going with the presentation. So who we are, we're driven to basically, the inception of Photonics was to faster communication, faster learning, faster entertainment. So by creating advanced silicon nitride integrated circuits. So from the inception, from the starting of Photonics, our focus has been on silicon nitride photonics Okay, Lucas says that he can't see the screen. Okay.
I think it's showing up fine on my end.
It's showing.
I can also see the screen.
Okay, Lucas. Okay, I'll keep moving forward. Hopefully, Lucas, you'll be able to fix that. Silicon nitride photonics with MEMS, basically. So Eponics was founded in 2012. We are located in Montreal, Quebec, Canada, now with 39 employees, and we have a patent portfolio exceeding 27 patent applications, for which already more than 20 have been approved. In the making of Eponic, we've been able to access up to over $42 million Canadian, mix in half of equity and also support from the multiple government. The key markets we're looking after for our product are in the telecom and datacom space. And more recently, we start working on opportunities with partnership in the area of quantum sensors, I should say. So the making of Eponics, how did it start? It's, as mentioned, we were founded in 2012. Selling telecom equipment at the beginning from existing supplier in Korea. And talking to customers came out some needs for more data, lower power, and lower cost, which is the requirements and the eternal needs of the telecom world and the data center as well. So in 2014, by accident, in an activities organized, I think that was by CMC or the C2MI, we met two scientists from Université du Québec à Montréal, Professor Nabki and Menard. One was working on MEMS and the other one on silicon photonics. They were good friends and wanted to work together and present to us the idea. So we basically went to see and prepared with the NSERC and also with collaboration with the ETS and also the financial support locally in Quebec of Prima Quebec and Prompt Quebec. We created first collaboration project formally recognized by NSERC. Initially at that time, they were Engage program and formal CRD program that were slowly being put in place over time. Then, with the idea, we started working in multiple university fabs at McGill. We've been doing some activities at Polytechnic and University of Sherbrooke, 3IT, and but also a lot at INRS in Varennes, working on MEMS processes on one side, and on the other side, we're developing the silicon nitride photonics capabilities and expertise. So basically working in the university fabs with the goods and the bads of some of these environments. Then we extended the multiple partnership. At one point of time, we've been able to get an interesting grant from SDTC Canada that enable us to get the development to another stage. So at that time, we expanded collaboration, working with Université Laval, Concordia on some design in silicon nitride photonics. We integrated CPIC Fab with UBC, obviously, at that time in the making of and going through the multiple collaboration. Then, at one point of time, we got to some kind of working prototype for optical properties, but basically fair enough as a process to be able to start working with the C2MI in Bromont. That was in the years 2016, 17, I would say, where we started the development on one side, on the chip development and the process development of silicon nitride and MEMS. Thanks to the C2MI, at that time, we've been able to increase the support from the multiple government, thanks to NCE and the federal government Center of Excellencies. and also with the Quebec government on the PSM numeric initiative. So moving forward with the collaboration, accessing more and more financial supports and extending the level of partnership and maturing the technology, getting to the point of having working samples and a prototype. That led, by the way, more recently, the recognition by ADRIC. ADRIC is a Quebec-based organization who recognize the good examples of collaboration processes, and that was a recognition of Photonics as being a good collaborators, not only in Quebec, but I mean even up to British Columbia with UBC and Professor Krastowski, who will be talking very soon, and more recently from the chip. Having a chip was a good thing in semiconductor, but the next step is to work on optical packaging. Optical packaging represents a good set of challenges. So we've been working over the years on multiple technologies and ending in discovering at the early time where UBC decided to buy a Vanguard machine and install photonic wire bonding at UBC was kind of an eye-opener. In parallel, we've been working with Vanguard for many years in developing the photonic wire bonding technologies. And later I'll be explaining a little bit more on photonic wire bonding and suspect that Professor Krastowski will also probably cover about that. But we've been doing a lot of work on developing the capabilities around photonic wire bonding, thanks to UBC, thanks to the support of REMAP as well, where we've been able to co-found a project to staff resources in UBC related to photonic wire bonding. So that was it is a great success. We've been able, thanks to Lucas and UBC and Vanguard, to develop all the toolkits that I'll be showing to you soon about optical packaging of integrated photonic devices. So a die with the proper optical packaging, and the next step is going down the hill to production. So now we are working with the very large MEMS foundry, where we have ported all of the processes around silicon nitride photonics and MEMS, and having the capabilities and building the partnership around the C2MI ecosystem in Bromont to build fully the device. So some of the devices were completely built in Bromont, exception of the photonic wire bonding machine, which is available, that is available at UBC and also in Germany. More recently, this winter, an announcement was done by the Quebec government regarding zone d'innovation, innovation areas in the province, where basically the C2MI has been identified with Technom as one of the two innovation collaboration areas in the province with significant investment moving forward. So it has not been announced yet, but I can tell you that a photonic wire bonding machine in the technology will be also installed in Bromont and will be available to Photonics and but also to the overall C2MI ecosystem, and being able to build 100% build product in Bromont thanks to that investment. So a few words on our technology. So as I mentioned to you, we're a silicon nitride-based company with MEMS. So this is really our core competency. Everything we've done over the years was silicon nitride related. When you're looking at the overall integrated photonics, this is I'm showing here a table created by LAB2FAB demonstrating some of the different technologies for waveguide on silicon nitride. At Photonics, our key focus in being able to combine the MEMS with the waveguide, the silicon nitride waveguide, we're basically working on buried structure on silicon nitride, but with the where typically results range in the 1 dB per centimeter-ish, depending on the wavelength. More recently, with our MEMS foundry that has superior capabilities, we've been able to consistently achieve and lower than 0.4 dB per centimeter on waveguides. As I mentioned, that can be co-built and integrated with movable MEMS component. The benefits of silicon nitride are well known in the industry with the good bandwidth, the low loss, no noise, good temperature range available from the material, leading to interestingly small and nice sizes of device from the economical point of view. With everything integrated, being built in as part of our manufacturing process of the chip, being ready and thought about for hybrid integration, and I'll be covering that. And obviously now porting this in the MEMS foundry is making such that this year we're capable to release our first commercial product to the market. So when I was talking about hybrid integration, I mean, silicon nitride has many benefits, but basically also some drawbacks. As an example, it's not, well, it's not readily available in foundries to have heterogeneous integration of laser or bonding of laser component as part of the silicon nitride. So the silicon nitride platform is really passive, but with the material and the lower losses make it well suited for hybrid integration. Using chips based on silicon nitride photonic with MEMS and hybrid integration. We've been working on multiple technologies over the years to do hybrid integration. We've been doing active alignment of fiber optics, of laser and photodetector as well. But over the years, with the assistance of LAB2FAB and also Vanguard, we've been able to do the hybrid integration of lasers, SOAs, amplifiers, using photonic wire bonding, fiber attach, obviously. Photodetector is a technology that we master well. We typically do direct coupling of waveguide to APDs in some of the assemblies technique that we develop to maintain a very low loss connectivity to photodetectors. But obviously, the possibility to do with photonic wire bonding, the door is open for chip-to-chip as well. So the capacity to take silicon photonics device to combine to silicon nitride device is definitively possible with the usage of photonic wire bonding. We also gain and develop the expertise to combine free space component with integrated circuits. Some of the component in the industry like circulators and some filters are not necessarily available or available for integration with photonic integrated chip. So in this case, often the capacity to co-locate free space and integrated circuit is an expertise that we develop in mixing and building these hybrid systems, having in mind fast prototyping, which is now made available and possible with the photonic wire bonding. This is basically the capacity to take existing off-the-shelf component, laser, SOA, APDs, best of breed or best components available, and to mix them together. Electronic packaging and building full product with the electronic per se, leading to a full product. Many type of application that can be explored and that can be developed with the technology. We focus on telecom and datacom, and in partnership with other companies, we're really exploring right now quantum sensors. Our know-how, our expertise is basically in the complete cycle of developing a product. So Photonics has the expertise to develop, design, optical component and silicon nitride component, have the chip design, doing hybrid integration and electronic, leading to a full product with the overall cycles available. So from design to qualification, it's really that full solution thinking that we're applying for some of our own product, but also the product that we will be developing for some of our partners and customers. This is showing here an example of photonic wire bonding to an SOA device. So it's from fiber optic in that case to an existing SOA. Yes, as I mentioned, it's really our capabilities to have a whole one-stop shop or complete approach in design and making of building a product per se. There are examples. This is one of examples that where we have been exploring not on that specific application, but on similar application where some companies have been developing prototype optical using optical or quantum approach with traditional optics, coming to see us to work on the process of building these complex systems and having them on a photonic integrated. So we're not quantum experts, but we have the capabilities to work with quantum experts, take these prototypes and work on photonic integration of these devices together, targeting application in this example on room temperature. Quantum require collaboration by definition. It's difficult to be at the same time an expert in quantum and in photonics, and partnership are very important. As a summary, this is who we are, the making of Photonics, and some of our capabilities and offering. Thank you so much.
For now, we're going to move on to our second presenter, who is Lucas Krostowski at the University of British Columbia.
Wonderful. Okay, great. I put my slides in the link just in case it's not working for anybody. So I'm going to speak about the Silicon Electronic Photonic Integrated Circuits program, which we've been running since about 2008. So we're running on, I guess, 14 years or so now. So it's quite a while. And so I'll give you a little bit of overview of what the SciPig program is and on an expansion into the fabrication parts, and describe a little bit of one of our exciting activities, which is on laser integration. And in this case, the LAB2FAB portion is talking about how we can go from lab scale research to gradually turning this into a commercial reality through an experimental multi-project wafer run. Talk about also photonic wire bonding, as Philippe mentioned, about the possibility of offering packaging as a service, and finishing with an upcoming workshops. So in terms of the SciPig program, in 2008, we started offering workshops, and the key what we've been working on is including fabrication as part of the training. And so the idea is that participants, either from industry or academia or government, come join us learning about the design part. Then they go home and do they design it, submit it for fabrication, and then the chips come back, and then they do their own testing. So we've trained about 500 people so far. And we run these workshops, both a passive and an active version of this once per year. And recently we have this online course as well, which is just passives. So a few years ago, maybe 3 or so years ago, we started the expansion into the fabrication. And so the idea here is this is a consortium that's focused on fabrication of silicon photonics. And there's a combination of universities and governments and companies and essentially the full chain, all the way from the design, all the way to packaging and test, and even up to incubation for startup companies. So our goal between both of these things is to help people develop ideas and then mature them, fabricate them, and then eventually turn them into industrial success stories. So we have a number of members as part of our consortium, both universities and companies, and we're happy to welcome more. So the way the consortium works is, I guess this is a circle, but we can start the circle maybe at the bottom here, where we plan new process development activities. And so we have internal process development activities, such as, for example, thinking about polymer modulators is something that we're working on right now, and laser integration I'll talk about. So we plan based on discussions in the consortium of what we want to do, and then we set a design date for it, and then create a fabrication run. So then LAB2FAB members, either at the universities or in companies or through some collaboration, there will be process development runs, experimental runs, initially just for the members, just to try things out, and then gradually, and then I guess eventually the members get chips back. We discuss results. We have meetings about those things, and this goes around and around, and then gradually these processes become more mature, and then they're going to be offered by translational partners and become commercial activities. And I'll show you with the example of the laser integration in particular here. So the laser integration, this is called the LAB2FAB Shuxton. So we have a code name for all our activities. So the goal here is to integrate lasers with silicon photonics. And the approach that we've chosen is to use lasers that you can purchase. And so the lasers we actually have access to cost anywhere from $1 to $3 roughly. And what's nice about these is that they've already been tested, so we know that they work. And it's a matter of flip chip bond, integrating them, attaching them, doing electrical wire bonding, and then photonic wire bonds. So this is an optical waveguide connecting the laser into the silicon waveguide here. And so we've been developing essentially the processes to do this little deep etch, to etch down 100 microns, put the laser in here, do the metallization on the bottom, and so on. And this process is working. We're getting coupling efficiencies greater than 50% from the laser into the waveguide on the silicon chip. And this is right now being done on a chip scale. And then what we'd like to do is gradually work towards delivering this on a wafer scale process. And so potentially you can populate 5,000 lasers per wafer. So the tools that we're using for this research activity is an electron beam lithography tool that can do up to 200 millimeter wafers. We can do also maskless lithography and etching. So this is all up to 200 millimeter wafers. And then photonic wire bonding. So this is basically an additive manufacturing technique where you're printing a polymer directly on top of your materials, and that polymer becomes the waveguide. And then we have more conventional tools like the flip chip bonding to attach the laser, and the electrical wire bonding. So this is a semi-automated wire bonder for packaging. So a few pictures of what this looks like. So this is a chip that was fabricated at UBC using ZEP resist, using this new etcher that was recently installed. It's an ICP-RIE etcher. And so you can see the definition here of the waveguides, and then this is the deep trench with metal on the bottom, and the laser pick and placed. And what's nice about this is you don't have to place the laser very accurately. Within 30 microns is sufficient, because the photonic wire bond tool has an image recognition software that can find the location of the two facets and then calculate and print the waveguide in the right position. And so here you have an optical waveguide connecting the laser to the silicon waveguide, and then on this side you have an optical polymer waveguide connecting the silicon to an optical fiber array. So then this allows you to test things like loopbacks and then connect the fiber to the laser. So this is the experimental activity, and then the translational activity is working with applied nanotools. So essentially developing the same process in applied nanotools. And here you can see these are edge couplers. So these are silicon waveguides with edge couplers and then photonic wire bonds attached. And this seems to be working pretty well so far. So this is results that we've been obtaining in the last several months. And so applied nanotools offers processes with passives and heaters and phase shifters, deep trenches, and so on. And we're working to make this compatible with this laser integration activity that we were describing. So we also have been developing, I guess, to help designers come up with their design, process design kits. So this is essentially documentation and libraries and models and examples for commercial tools and open source tools. So working with Lumerical, Cadence, Lucida, and K-Layout. And this PDK is actually open. You can download this yourself, and you can read all the documentation, find out about it. There's installation and tutorials and so on, and application notes on how to create a design that consists of a laser with a fiber and some circuit on board. A few months ago, we decided to make this a public activity. So we had in February a publicly available run where people could submit designs to CMC Microsystems, and the designs have been aggregated now, and they're going to be fabricated and hopefully delivered to customers this summer. So this is a collaboration of several members from the consortium. So Applied Nanotools is doing the fabrication. Dream Photonics is a UBC startup that's going to be doing the photonic wire bonding and then using this UBC Vanguard equipment. And we're running this as a kind of a standard MPW run where you get customers receive multiple chips, and there's a cost associated with it. So a number of organizations contributed to this activity. So going back several years, so there's funding from equipment, so from CFI, from the Stuart Blossom QMI Institute for clean room and so on, and then there's been funding from REMAP, as Philippe mentioned, and so this is really focused on the photonic wire bond development, and then there's been funding from SciPic and LAB2FAB consortium members to do a lot of the chip and laser integration work. And we also have the tool vendors and MPW aggregators that have been helping us assemble this whole thing. So it's really been a pretty large team effort to get this far. And we split up the roles in terms of different organizations have different roles. The designer creates a design. It goes to CMC for aggregation and invoicing, Applied Nanotools for chip fabrication, then Dream Photonics for laser attach, and then the designer gets the chips back in the end. A few words about optical and electrical packaging. So I mentioned that at UBC we have some of these tools, the wire bonder, the die bonder, and then we also talked about the photonic wire bonder tool. So there's an effort where CMC is taking the lead on a proposal called Fabric, and part of that is to offer packaging services. So this is an example of a package that we've been developing. So you can see here this is a chip. This is actually a chip from AMF in Singapore with optical fiber arrays. So this is, I believe, 2 8-channel fiber arrays glued down, then photonic wire bonds to the chip mounted on a little carrier. So this type of assembly and others is something that we'll be able to offer to the community through CMC Microsystems. Okay, so just to wrap up in terms of coming back to educational activities, over the next few months, we have a few exciting things. So the first one is 1 month from now, we have an online course. So this is an introductory course for silicon photonics, fabrication of basically just waveguides at Applied Nanotools and University of Washington. And we provide test results as opposed to delivering the chip. So there's no testing involved on the customer side. And in the active workshop, this is the more advanced, where we talk about PN junction modulators and germanium detectors and phase shifters and things. And this includes 2 fabrication runs, one with Applied Nanotools and then one with AMF in Singapore that has on the order of 20 mask layers. And also our partner EVA is doing some automated testing. So the registration for this is open, and the course starts on May 30th.
Our next speaker is Pierre Barini. He is the director for the Center of Research in Photonics at the University of Ottawa. And he's going to give us a short sort of 5-minute overview of the University of Ottawa's fabrication facilities. So Pierre, I'm going to hand it over to you.
Okay, I gather everyone can hear and see my slides.
Yes.
Yes.
Thank you. So in 5 minutes, we at the University of Ottawa have been building a nanofab since about 2008. And almost done. So if you've ever wondered how long it takes to build a nanofab in Canada, well, there you have it. It's close to 15 years. The axis in the creation of our facility has been to access the nanoscale. And so we've been focusing on the acquisition of a tool set that enables lithography at the nanoscale and that enables characterization inspections at the nanoscale. So I'll talk very briefly about our capabilities and the tool set and how we work with partners. So we have certainly a number of academic users. Most of our academic users tend to be professors that work in the area of photonics at the University of Ottawa. And there are many of us. We're close to 30 profs at U of O that call photonics their main area of research. And many of these professors have collaborations with industry. And by extension, the nanofab becomes accessible to industrial partners through those collaborations, but also it becomes accessible through direct memberships and direct access to the facility. We've worked with quite a large number of companies over the years, either directly as users of the facility. The facility is a user facility, which means that we accept users, we train users on the use of tools, and then we turn them loose. So grad students, for example, would spend maybe 3 to 4 months one-on-one training on some of our beam tools, for instance, and then they could run with it and carry out their PhD fabrication work in that context. But also industrial users can do the same. So we work with industry directly as users of the facility, or through contract fabrication or through research collaborations. The NanoFab is in our brand new advanced research complex, which is a $100 million building here in downtown Ottawa. It houses essentially all of photonics research at the University of Ottawa. So all 29 profs, for example, are co-located here with their labs as well as the NanoFab. We occupy about 250 square meters of floor space for the NanoFab, and so far about 20 million in investments, mostly CapEx, into acquiring tools for the facility. So yeah, all of these points I've mentioned already. We're essentially the only open facility in the region that has a nanoscale focus. And open access means really that we welcome internal, external users into the facility to carry out their projects with very little regard on what those users may be doing, in order to maintain data privacy, in order to maintain confidentiality of work, which is really in the hands of users. In terms of tool sets, well, we certainly have a good number of what you would expect of tools that you would expect to see in sort of a standard clean room. Yellow room with everything that's needed in there to carry out resist processing, optical litho. E-beam litho, we currently have the Wraith Pioneer, which enables us to get down to about 20 nanometers of resolution. We also have a focused ion beam system that works with helium. That helps us get down to about 5 nanometers. Some etching tools, some deposition tools, microscopy, a couple of AFMs. We have 2 SEMs. Our Pioneer can double as a SEM. We also have a Gemini 500 with an EDX detector, and we have also the ability to do microscopy with our helium system. New tools coming in. So these are tools that we will be installing over the next 5 years as the result of a CFI award that we recently won. So we'll be getting about 13 million in new tools invested. We have an MOCVD reactor that's been spec'd for 3.5 epitaxial growth, to be able to do lasers and indium phosphide based optoelectronics. ALD sputtering, LPCVD evaporator, a second evaporator, we already have one. 100 kV beam system is coming in as well to supplement our 30 kV Wraith Pioneer. Our Wraith Pioneer sees 24/7 usage and has seen 24/7 usage 365 days a year since 2008. It's the first tool we acquired, and since then it's been in continuous use essentially, except for changeover of filaments, apertures, regular maintenance. So the second e-beam system is certainly going to be quite welcome among our user community. The kinds of projects that have been ongoing in the clean room are basically essentially anything that you can imagine in photonics, from waveguides. We've done a bit of silicon photonics, though that tends to get done elsewhere with facilities that already have processes that exist. But some folks have etched some silicon waveguides in our facility with reasonable success. We've also done photonic crystal waveguides. We've worked with lithium niobate, with 3.5s, AlGas. Also lots of polymers, biosensors, metallic metasurfaces, which is sort of what's shown on this slide here. These are nano antennas that we can create, features down to about 10 nanometers over centimeter square-ish areas. This was a graphene-based project that we worked on with IBM Canada, where we put down metallic nanostructures on graphene for enhanced graphene light interaction. Here's a modulator project that was also the subject of an industrial collaboration. These modulators were destined to the test and verification market rather than the conventional telecom market. This is an optical phased array. So these are optical nano antennas that we can see here, very tiny, that are connected to a fan out to outside fingers for doing beam steering. This is also within the context of an industrial project. These are flowers for Mother's Day that we created years ago. They're holes arranged as heptamers in a metallic film. These holes are about 100 nanometers in diameter, and then this bridge in here is about 10 nanometers in width. And these are in a film that's about 50 nanometers in thickness. So these are fun structures. They're nanohole arrays that we create over quite large areas, including actually on fiber tips. So we cleave an optical fiber, evaporate a metal on there, and then do this nano fabrication directly on the tip of an optical fiber. And then these things work well as optical sensors. So on tips of fibers, you can put it, in people. Not that we've done that, but that's sort of the goal, to create endoscopes and in vivo biosensors on tips of optical fibers. And so that's kind of what motivated this project here of creating these nanohole arrays. And really the focus, as I mentioned earlier, is and has been and continues to be on nanoscale features, the definition of nanoscale features, as well as the characterization of nanoscale features, seeing what you have, and seeing what how the structures would behave. We work with industry, we work with academia. We have very conventional access models, fairly conventional access fees as well. So two places where the facility has been of strong interest to industry is in the context of collaborative research. So a company will work with one of our researchers under the proviso that our researcher has access to the facility and can do prototype development and device fabrication. So that attracts industry to our researchers and to the university. The other place where we've seen a fair bit of industrial use has been to directly access our tools. Much of the local industry in Ottawa is fabless. So companies get their stuff fabbed elsewhere, and then they receive wafers with their devices on, their diced wafers, let's say, with chips, sometimes even packaged stuff. And, the chips don't work. And so companies need to understand why the chips don't work. Sometimes it's a fabrication problem, sometimes it's a design problem, but in sort of reverse engineering and troubleshooting their gizmos, they need access to high-end microscopy facility. And the helium system that we have, which allows milling as well as microscopy, is really state-of-the-art. It provides better resolution than a SEM does. We have both. We have also state-of-the-art SEM. And for the really fine imaging work that's required, we use the helium system. And that's kind of where industry has found its interest. It's in accessing our microscopy tools to help them debug the chips that they've had fabbed elsewhere that don't work, or that are not working as well as they should, or that are showing low yields or whatnot, to try and understand whether they in fact received what they ordered from their supplier. And so that's kind of the second axis where industry tends to access our facility. And they do so as users. So they come in with their chips, and they can get trained on the use of our tools, look at their stuff, take away their data, and then go and analyze their data elsewhere. without having to divulge any intellectual property. But this comes, of course, for a fee. So we charge industry to do that. And oftentimes they'll require help and assistance from our technical staff, which we have. And they can have access to that technical expertise as well as needed. So I'll stop here.
Excellent. Thank you so much, Pierre.